Good morning and welcome back. So today we'll take a look at the second part of the lecture notes in this lecture and a couple of other ones. And so in the first part of week 3 we took a look at probability. In the second part we'll look at the next idea, which is random variables. We'll look at discrete random variables to start off with. So the idea here is this. A random variable is nothing more than a map from a sample space to the real numbers. And a simple example is I toss a coin once and let x equals 0 if x is heads and x equals 1 if x, actually I mean 1 here, let x equals 1 if x is a head and x equals 0 otherwise. So x is a random variable. Its value depends on the chance of tossing the coin. Probabilities here actually come from the sample space, so we know probability of getting a head is 0.5, so that means probability x equals 1 is 0.5, and probability x equals 0, which corresponds to a tail, is also 0.5 if the coin is fair. There are two kinds of random variables that we deal with in probability: the discrete random variables and the continuous ones. So discrete random variables usually take only certain fixed values, and they usually come from some kind of counting process. Continuous ones actually arise from some measurements usually, and they take values in some interval. Now those are the differences. And the idea of random variables essentially is that there are many examples and many situations which might look different to us from the outside, but when we look at the underlying random variable idea, they become the same. And the idea of random variables also is that we can't deal with sample spaces so easily. Random variables actually transform things to numbers, and then we can apply the full power of mathematics to that to get all the results. So, as we said, a discrete random variable is one that takes only certain fixed values. If we toss a coin twice and we let the random variable x denote the number of heads tossed, then x can take the value either 0, 1 or 2, and the probability of getting no heads means I've got 2 tails. Now I'm assuming independence over here, so that means my outcome space here is going to be 2 tails, a tail and a head and a tail, or 2 heads, and all of those are equally likely. So probability that we have x is, I mean probability takes about a 0, 1 and 2 over here, actually, sorry, my apologies. So x takes the values 0, 1 or 2 because I'm tossing the fair coin twice, and so x equals 0 corresponds to 2 tails, this is a quarter, 1 out of 4. X equals 1 corresponds to either this or that outcome there, and that's 2 out of 4, and x equals 2 heads, or x equals 2 is 1 quarter again. Now this notation here essentially means probability that the large letter x here takes the small value x here, and we denote that by what's called the probability mass function. This is a p, small p here, and the subscript x here denotes its random variable x we're dealing with, and this is the value the random variable takes here, or realized value, what we observe here. So get used to the notation here, but if you don't, you can live with it, you can survive without it, but it's important to get the notation right here. The mean or expected value of a random variable is essentially what we call the mean, or the average value, if you like, in some ways. And the way it works is, all we do is take the values that the random variable can take and multiply this with the corresponding probabilities, and then this sigma here means sum, so we add them all up. We do this for all values of x. For the coin tossing example, if I toss a coin twice, the value 0 has probability 0.25, the value 1 has probability 0.5, the value 2 has probability 0.25. If I work them all out, I get 1. In other words, if I toss a coin twice, I expect to get 1 head. Now, given that the probability of heads is a half, that means if I toss the coin twice, half of them should be heads on average, and that makes sense here, so I get the average here as 1. Now, this is if I want the mean or e of x over here, but if I've got some other function here instead of just x here, for example x squared, nothing changes. All that happens is because I've got x squared here, Now square the values and then multiply with probabilities. Square the one and then times probabilities, and so on and so forth. In this case, if I calculate this, I get 1.5. So you might wonder why I'm going to work out e of x squared. We'll see the reason for that later on. The variance of a random variable is worked out this way. From it's e of x squared minus the mean all squared. And its square root is, again, less than the deviation as before with data. So for the coin toss example, you've just worked out e of x squared, and we know e of x is 1. So the variance here is 1.5 from my previous calculation, minus 1 squared, that's 0.25. And the standard deviation is a square root, which comes to 1.7 or so. Now, we know that variance is a measure of spread. Standard deviation is also a measure of spread, and it's a better measure because it's in the same units. Remember that the variance deals with square things. So if I'm looking at the number of heads, this is heads squared, doesn't make any sense with the variance. But if I look at the standard deviation, that means on average, that means essentially this gives me the spread in terms of heads here. How many heads, which is much more sensible. Example here, the mean and standard deviation of this distribution. So we know that the mean here is going to be equal to, as we had before, the values times the probability, so it's negative 1 times 0.1 plus 0 times 0.2 plus 1 times 0.3 and then plus 2 times 0.4. So that's negative. Forget the decimal 0.1 for example, just negative 1 here, and plus 3 is 2, and this is 8, 8 plus 2 is 10, and I put my decimal place back in there and I get 1.0. To work out the variance, I require e of x squared. So now I square this, then multiply with probability. The next is going to be 0 anyway, and again 1 squared times probability, and then 2 squared times probability. Again I can ignore the decimal point. So that's 0.1, that's just essentially 1, and this is 3, which is 4, and this is 4 times 4 is 16 plus 4 is 20, so this comes to 2. And so the variance of x from my calculations so far, I know this is e of x squared minus the mean all squared. So that's 2 minus 1, which is equal to 1. And so the standard deviation is the square root of variance, which is also equal to 1 in this case. So that works out quite nicely. Another example, grizzly bear litter sizes are between 1 and 5 cubs, although litters with more than 3 cubs are rare. From data collected by Schittler and Hetzel. This is in an article there, in the excuse me, in a book here actually, and so this is a real article. They estimated the probability of litter sizes as follows: 11% were single cub litters, 50% were 2 cub litters, 39 were 3, and 2% were 4 cub litters, and 1% were 5 cub litters. Now it says calculate the mean and variance, and then the second part says ecologists determine or estimate that for a viable population of grizzly bears, the number of cubs should not be lower than 2. Is this population of grizzly bears viable? So here we first of all define ourselves a random variable. It is simple in this case, it's obvious. So we let the random variable x denote the number of cubs in a litter. We now want a distribution. The distribution has been given to us in the question, so all I'm doing is putting the numbers together. So 1 cub had probability 11% or 0.11, 2 was 47%, so that is 11% single cub, 50% 2 cub. So I've got the numbers wrong here in fact. What's going on? Let me see if this adds to 1 here. So that's 39, 40, 50. Oh, this is right, 0.47. So this number here is wrong. It's not 50%, it's 47%. Alright, so the mean number of counts per liter, the calculation is 1 times 0.11, 2 times 0.47, and so on, and that comes to 2.35, and EMF squared here works out to be apparently 6, but I think it's 6.07 here, just go to the scale here, so it's 6.07. And so the variance is worked out as usual, so is the EMF squared minus the mean squared, so it's 6.07 minus the 2.35 squared, and that comes to 0.5478, and the standard deviation is 0.7399. Now, the question further asked is, what we were told is that the mean number of cubs, or the number of cubs, should not be lower than 2, otherwise the population is not viable. So in this case, the probability of getting less than 2 cubs is 0.11, and the mean number of cubs is 2.35, and the standard deviation is 0.739. So it's not very likely that the number of cubs is less than 2 here, because the deviation here is, well, it's fairly large compared to 2.35 in some sense, but looking at probability as well and basing on this these two numbers here, it's rather unlikely the number of cubs is less than 2, so this population seems to be viable. Alright, we'll stop there with this and carry on in the next lecture with Bernoulli distribution. Thank you, bye.